Righto. Thanks for hanging in there till the last session on the last day. And I'm going to be talking about some work that I've been doing, which was led by Catherine Collier, on defining desired state of seagrass as a management target on the Great Barrier Reef, and also wanted to acknowledge the co-authors, Mike Rashid and Rob Coles, who are also in the audience. So seagrass meadows form a major habitat on the Great Barrier Reef. They have incredibly high value as a food for iconic species like green turtles and dugong. They provide fisheries habitat, a nursery, and also a range of ecosystem services. They also have really high diversity. So if you look at the photos here, you can get some kind of idea of how different they look in terms of the biomass and the morphology. So we have at least 12 seagrass species on the Great Barrier Reef. But when it comes to the communities where we find seagrasses, they're often a mix of multiple species. So you do get monospecific communities, but multi-specific is much more common. And the species that are present in those are often defined by individual species environmental constraints. It's also important to consider when evaluating seagrass, especially as a manager, is that they often exist in these cycles of decline and recovery. So this figure here shows a healthy seagrass meadow on the left-hand side of the Esplanade in Cairns, and then a couple of years later on the right. And that decline was marked by a period of intense La Niña periods that we had in 2009 to 11, which was really bookended by Cyclone Yassi. And we had a huge amount of seagrass loss along the east coast. So because of this diversity and also the spatial and temporal variation in which seagrass meadows exist, setting ecological targets and assessing management success is not going to be an easy or a simple process. And to even begin to manage seagrass, there's some really fundamental questions that need to be answered. So these are things like, what do the reef seagrass communities look like? Where are they found? And then also, what is their desired state? And the objective that we had in NESP 5.4 was really about looking at defining the desired state for as many of these communities as we could on the Great Barrier Reef. This project, though, was really a follow-on from NESP 3.2.1, where we did a similar activity in Cleveland Bay, so much more localised scale, and then also NESP 3.1, where we created the initial seagrass data synthesis. So today what I'm going to do is walk you through the desired state framework that we created for these projects. And there was 4 steps which I'll walk you through. And the first of which was synthesising all of the available seagrass data that we could get our hands on, then modelling potential seagrass habitat, classifying seagrass communities within that habitat, and then defining desired state. And when we're talking about desired state for seagrass, what I'm talking about here is biomass, which is one of the key indicators of seagrass condition. And then I'll just wrap up with a couple of the outcomes of the project and applications. So the first step we had was to synthesise all of the seagrass data that we had available to us. And this resulted in a composite with 35 years worth of data and more than 81,000 individual sites. You can see this data set is presented here as seagrass presence and absence, where presence is the green dots. And this is available as a shapefile on eAtlas, so you can download it, and will also be coming out soon as a data publication. The next step was to model the potential seagrass habitat. And so here we used random forest models looking at seagrass presence and absence. And then we used a huge amount of environmental variables, many of which we know are likely to impact seagrass. And so I've just got a whole lot of maps with different environmental variables there. A lot of those came from e-reefs. We also had things like depth and tidal exposure. And what that created was a model of potential seagrass habitat throughout the Great Barrier Reef. Rob Coles will want me to point out that this is not a map of seagrass meadows. It is different levels of probability of where we could find seagrass. And we had quite a low threshold in terms of potential habitat, which we defined as above a probability of 0.2. And the reason for that is that it tended to capture these really ephemeral deep water seagrass sites. But what it also allowed us to do was look at areas which are in grey here that were really unlikely to have seagrass, and often they were the deeper water areas. So we're able to exclude that from the community analysis. And again, you can download this as a raster from eAtlas. The next step we then had was to define the seagrass communities for the reef. So we looked at areas of potential seagrass habitat, which is everything here from yellow through to dark green. We then looked at the site data, but here we were looking at individual seagrass species, of which we had data for 12 of those. And then we looked at those same environmental conditions throughout the reef. And when we put that all together in 6 different models, what we found were there were 36 unique seagrass communities throughout the Great Barrier Reef, and this includes going into the adjacent estuaries. So we defined the models according to reef, coastal and estuary, and also intertidal and subtidal. And again, you can get this from eAtlas. Two of the things I wanted to point out with this community analysis is the reef subtidal, which are those green communities, were by far the biggest in terms of spatial footprint. So, and these also are really the ones that we have the sparsest data for, the oldest data, and very little monitoring happening. So they cover the biggest area, but we know the smallest amount about them. The other thing I wanted to point out was that Hinchinbrook Island really stood out, particularly among estuarine seagrass communities, as a really important area in terms of community diversity, but also as an important transition zone between more southern regions and the more northern region of the Great Barrier Reef for seagrass communities. And again, there's very little monitoring that goes on there. So within our 36 communities, 8 of those were reef communities, and we had different things that drove the divisions between community types. So for the intertidal meadows, we had benthic light, sediment and wind speed, and in the subtidal, we had depth and water temperature. There were 13 coastal communities, and again with different environmental constraints. So water temperature and water type, salinity and tidal exposure in the intertidal, and then current speed, depth and sediment for the subtidal. And then in the estuaries, we had 15 communities, and for the intertidal, tidal exposure and latitude were important, and for the subtidal was depth and latitude. But what I want to point out is that something which really surprised us was how little environmental data there was in the estuaries that we could use in these models, and particularly environmental data that was consistent across all the estuaries within the Great Barrier Reef. And the e-reef models generally don't travel up into the estuaries, and we couldn't extrapolate or interpolate up into them. It wouldn't have been appropriate. So latitude comes out as important, but what this really is a proxy for a whole lot of other environmental conditions, and we just didn't have the data available to be able to include those in the models. So our fourth and final step was then to establish desired state of biomass for these communities, and this is really as an aspirational target for guiding management decisions. We use the ecologically important indicator of seagrass condition being biomass, and we looked at data that was available from 1995 to 2018. So prior to 95, it generally was percent cover data. This is a little bit more technical than I know most in the audience would like, but what we did to define desired state was to use a reference data set. So we looked at the maximum biomass year and then all of those other years that were statistically similar to it. So these are the years with the asterisks. And then what we did is calculated the mean and the confidence limits around that. And then we defined whether or not a meadow or a community had met desired state within a given year if it fell within those confidence limits or above. So I'll just run through a couple of examples from the different communities. And so you've got estuarine, an intertidal community on your far left, and then a coastal intertidal community. And we had much richer data within the coasts and the estuaries compared to the reefs. So some of the things that really stood out was that across heaps of these communities is that you had this decadal style pattern of peaks and troughs. In particular, and this was almost across the board, you had these really big biomass peaks happening in 2004 to 2008, And then you had this really steep decline in biomass below desired state around 2009 to 11, and that coincides with those La Nina years and Cyclone Yasi. Then between coastal and intertidal, you had slightly different patterns of recovery. So for many of the coastal intertidal meadows, the desired state has returned, but in the estuaries this isn't the case. So many of these estuarine communities are still struggling to reach desired state since those declines a decade ago. The last thing to mention is that when it comes to the reef communities, is that we had a really small amount of data to go off. So we're quite stringent in terms of what data we would allow in for a given year. So we had a set of sample sizes required, and then also how many years of adequate data we would allow before we would define desired state. And so what this meant is for the reef communities, we had, I think, only 2 of the 8 where we could define this. So most of the reef communities look like this. We've got a bit of data, but we obviously need a lot more. So this is the reef subtidal one, which makes up the majority of our predicted community for the Great Barrier Reef. And yeah, limited data. So the outcomes of these NESP projects have been that we have distilled a huge amount of complex information into something which we think is really useful for managers. There's 36 communities, so it is still complex, but a whole lot less complex than when we started. So we think this is a really good starting point. The data's all available on eAtlas, so you're free to go and download it and use it. And we've also defined the desired state for many of the communities, and that's also available to download that report. So what we have discovered through this process is that there's this historical cycles of decline and in many cases recovery on the Great Barrier Reef. We've also identified knowledge gaps, particularly around the condition of these reef communities, and also really limited in what we can say about environmental conditions that the estuarine seagrass communities need to flourish. And also importantly, this is a really scalable approach. So we started off doing this for Cleveland Bay, and then we ambitiously thought, let's scale it to the whole Great Barrier Reef, and we thought that seems easy, and actually it kind of was, which was, you know, I think in retrospect probably optimistic, but surprisingly nice, is that we could extend this out to the reef using the same approach, and we would love to continue that further. So some of the current applications for this work is that it's already been incorporated into setting ecologically relevant sediment load targets for the Burdekin, and this is the work that's been done on desired state in Cleveland Bay. We've also been working on some species distribution models and benthic light thresholds and catchment management scenarios. So the one and only poster at this conference is over there on this beautiful big Baroque mirror, and that's the work that we've been doing with Barbara Robson, so looking at catchment scenarios and what that means for seagrass distribution. And also some of the earlier stages of this work were brought into the program design for RIMREP and the Seagrass Expert Group in advising on where data gaps are and where monitoring should be prioritised. Sometimes this doesn't like to go. Right, I also wanted to point out that this work was only finalised a couple of months ago, so I'm just going to do a bit of a plug of where we would like to see this work go in the future. So obviously, with 36 communities, it's a lot more complex than when the Great Barrier Reef Marine Park was zoned in 2004 with the bioregions that were classified that had seagrass involved in those bioregions. So any future spatial management of seagrass, we really hope that this work is included. This is also really important when it comes to understanding the exposure to risk and threats for seagrass. So obviously those things that are likely to threaten estuarine communities is very different to what's happening in the deep water reef communities. As I mentioned on the last slide, we'd love to connect this work into other regions. So we do have a lot of seagrass data for Torres Strait. We're working in the Gulf of Carpentaria now, and we've also got data from Harvey Bay. So we would really love to see this extend beyond the Great Barrier Reef. And then the last thing to mention is that I think this would be really useful in designing restoration programs, because we now know if we go into an area where there is no seagrass, we can look at, you know, the kind of potential that there should be seagrass habitat there, what species are most likely to also flourish there. And then within a much smaller area, you could look at an intertidal bank and make decisions around what communities are best suited for different tidal exposures, for example, or different depths. So that's it from me. I just wanted to say thank you to NESP for funding all of this work, and also Barbara Robson and Emma Lawrence have been really helpful with the modelling over the last year or two. That's it, thanks.